I'm working through chapter summaries for an introductory physics course, and I saw this problem, and I wanted to do it because it's kind of fun, and it comes up it doesn't really come up quite a bit. I had to slide about that. Okay, but I just want to do it, and that's the end of the story. So the question is, what's the acceleration of an object that rolls down an incline angle theta? And I use theta over here, but that's fine. And let's say this object has a moment of inertia of I. It could be anything. It doesn't really matter. It could be a sphere. It could be a cylinder. It could be a hoop. It could be some other unique situation. And I want to find the acceleration. Okay, so let's review some of the big ideas so far. Number one, we have Newton's second law. This says that the net force acting on this object is the mass times acceleration. I'm trying to find that acceleration. Next, we have the idea that if this is moving down the incline and rolling, then for a rolling without slipping, the following must be true. The velocity has to be related to the angular velocity, right? So the velocity of a rolling object has to be equal to the radius of that rolling object times the angular velocity of that rolling object. And this is a scalar equation. Also is true, the acceleration has to be related to the angular acceleration, r alpha. So if this is, just imagine this thing rolling. It starts rolling and faster and faster and faster. It's spinning faster and moving faster. So the acceleration is related to the angular acceleration. Well, how do you make an object have an angular acceleration? That's where this comes in. This is the scalar version of the angular acceleration equation. The total torque on an object is the moment of inertia, which could be anything right now, times the angular acceleration alpha. And then we define torque. This is a scalar version of torque. It's the force applied, the distance from the force to the point, and we've got to pick a point to calculate the torque, which should be the center, since we're doing with angular acceleration around the center. Times the sine of the angle, and this is the angle between F and R. Okay, let's get to it. But I want to do this. I want to do three things. I want to do a block sliding down an incline. And then I want to do with no friction. And then I want to do this problem. And then I want to do it another way. So I'm going to do this two ways. So let's start with this situation. A block down an incline, because everyone's done this. I'm going to actually do this one two ways also. So here's my block. There's no friction. This is the angle theta. So the first thing we're going to do is to pick the forces, write down the forces acting on this. So in a free body diagram, and if I don't care about rotation, which I will in just a second, if I don't care about rotation, then I can draw all the forces acting at a point, and I have two forces on here. I have a long-range force, which is the gravitational force pulling down. I'll call that mg. And then I have a contact force, the normal force pushing up like that. The next thing I want to do is to pick my x and y axis. So I could pick the x-axis this way. That would make sense, right? But if I do that, then I'm going to get an acceleration in both the x and the y direction. So a much simpler thing to do would pick this as the x-axis, and then this is the y-axis. So with that, I can draw my diagram. I'll just draw it this way. Here's x. Here's y. So I have the normal force up. And then I have gravity at an angle. And then you can do a little geometry here. If this is the angle theta, this is the complement of the angle theta. And so this would be the angle theta again. So this is the angle theta, and that's mg. Now you could do this. I could say F net y, that's a y, is equal to 0. And then that would say n is the y component of that force minus mg cosine theta is the y component of this, right? Because it's this part right here. That's the y component. And that'd be 0. But I don't really care. Who cares about the normal force? Do you care? I don't really care. Now I can do F net in the x direction, which we do care about. And you'll notice that the normal force has no x component. There is an x component right here for that force. It's going to be equal to mg sine theta. And that's max, right? So remember, the sine gives you the opposite part of that triangle. Since this angle's derived from or measured from the y-axis, we're using sine. And then I can just solve for a divided by the mass, and I get a is G sine theta. We're going to use that later. But why doesn't it rotate? Why does a ball rotate or a sphere rotate and the block doesn't? Let's draw this diagram a little bit again. So here's my box. And I'm going to draw the gravitational force acting at the center. That's actually okay, because gravity actually pulls on all parts of the box, but that's equivalent to gravity pulling at the center of gravity. Technically the center of gravity, which if the gravitational field's constant would be the center of mass. So the center of the block, if it's a uniform density, is the same as gravity pulling on all parts of the block. Now, what about the normal force? Where does the normal force apply? Well, if I apply, I'm going to put the normal force right here. I'm going to put where it's pushing. Then I have the same force diagram as above, but what's the net torque about that point? Well, the net torque about that point is going to be 0, right? Because this force has no torque because it has an R value of 0. It passes through the point of rotation. That's the point O. And so does this one. So it's going to be equal to 0 plus 0. So there's no torque, no angular acceleration. Everything is happy. Now, if there is friction, if there's a frictional force, and I put a frictional force right here, F friction, so it's sliding with friction, there would be a torque, right? Because now this force is going to exert a torque, and it would make it rotate that way. But it doesn't rotate because this normal force can be applied anywhere along the surface. So I actually could get a situation like this. I'm going to draw it carefully. mg is down right there. What if the normal force is applied right here, in, and the friction force is right there? I'm going to move it up a little bit. So now this force is going to make the block want to rotate this way. But this force is going to want to make the block rotate that way. So you can actually find the location at where those two forces are applied to make the torque equal to 0 due to these two forces. Now, of course, one more situation. I know this is about rolling, but if you have a really tall, skinny block, then it's possible that the normal force, even if applied at the very edge, and the friction applied at the edge, is not enough to overcome this gravitational force, and it can tip over. But you know that. You know blocks can tip over. Okay. So this is the only one that's important because we want to compare it to later. Now let's go back to the rolling object. I'm just going to draw it like this. So what forces are acting on this object? Again, I have the gravitational force. I'll draw that right here, mg. Now, I do need to apply where these forces are at. I have this one, the normal force, and I have this one, the frictional force. Okay, so let's draw two things. I need the free body diagram, and again, I'm going to have this as the x-axis, and this is the y. So in the x-axis, I'm just going to write it down. We're all adults here, right? Or at least I pretend to be. F net x is going to be mg sine theta. That's the x component of the gravitational force minus the frictional force, which is in the x direction, negative x direction. And that's going to be equal to m, I'll just call it ax. We're the acceleration in the x direction, so that's fine. Okay, now you might want to say, hey, I can find a magnitude for that. I can say the frictional force is the coefficient of static friction times the normal force, and then find the normal force from the F net y. It'd be n minus mg cosine theta equals 0, since it doesn't accelerate this way. That's wrong. Because that tells you the maximum friction force. But this friction can be anything between 0 and that value. So we actually don't know what the frictional force is from this equation. We don't know. You could find the maximum, but you can't know. So up here, I'm just going to leave that as friction. I don't know what it is. That's fine. I don't know A. Okay. Now let's write down the torque equation. Torque net O. So let's call that the point O. So what forces exert a torque about this system? Well, gravity does not exert a torque, right? Because it passes through the point of rotation. So it's like pushing on a door handle on the hinge. It won't rotate. And the same thing's true for this normal force. It has to be right here, and it has to pass through the center for two reasons. One, that's the only contact point. It's a circle of some type. And it has to be perpendicular to the surface. So that means it has to pass through. So both of these are zero torque. And then what about this one? This one would be a torque that would be the distance from that point, which is going to be R. I'm going to use capital R for the radius of the circle. And then the friction force, F friction, because time is technically sine of pi over 2, because the angle between R and F is pi over 2, and that's 1. And you could say this is going to be negative, and that's fine. I don't really care. I'm only worrying about the magnitude, so it doesn't really matter. And this would be equal to I times alpha. So let's write that out. R, friction force, is I alpha. But if it's rolling without slipping, then alpha has to be A over R. So from this, I actually can solve for the friction force. So I get F friction equals I alpha over R. And then I'm going to plug in alpha is A over R. So I get I A over R squared. Now I can take this and put it in up here. So I have, let me rewrite that equation. I get mg sine theta minus the friction force, which is this, I A over R squared. Yeah, that's right. Equals MA. Now I want to solve for A. So let's move this term to the other side. Let's start a new piece of paper. So I'm going to just write that equation right here. I have mg sine theta minus I over R squared A equals MA. How about that? Okay. So if I add this term to both sides, I get mg sine theta equals MA plus I over R squared A. And then I can factor out the A. So I have A times M plus I over R squared. Now I just divide both sides by this. But before I do that, I'm actually going to divide, just get it in the equation in the form that this textbook had it. I'm going to divide both sides by M. So I get G sine theta equals A. And I'm going to divide by M. I'm going to bring it in here. So I get M over M plus I over M R squared. So this is going to be equal to A times 1 plus I over M R squared. Now I just solve for A. I get A, divide both sides by this. I get A equals G sine theta over 1 plus I over M R squared. And that's the answer. And you'll notice that since this term on the bottom is going to be greater than 1, let's check the units first, actually. So G has units of meters per second squared. Sine theta has no units, right, because it's a ratio. And then 1 has no units. I has, remember, I is the sum over I, MI, RI squared. So it has units of MR squared. And, you know, the moment of inertia of a disk is 1/2 mr squared. The moment of inertia of a hoop or ring, that's a hoop, is just mr squared. But it always has that mr squared in there. So I can get mr squared over mr squared, which is no units. So I get no units on the bottom, and so I get acceleration. That checks out. Now, this I has to be positive, m is positive, r is positive. So this whole term on the bottom is a number greater than 1. So the acceleration for a rolling object is going to be less than g sine theta, which was the acceleration of just sliding object. So that makes sense too. And then the greater the value of I, the lower the acceleration. So if you have a disk, we'll get to the bottom, we'll have a greater acceleration than a hoop. Okay. Let's do this one more way, because in a physics lab, and I remember my physics lab, we didn't derive the acceleration. What we did was say, what object is going to be going the fastest at the bottom of a incline that's rolling without slipping? Omega. And so it's going to start up here from rest, and I want to find its velocity down here at the bottom. And then I'm going to use that to find the acceleration. So it has an incline of angle theta. This is at y equals 0, and this is some distance s. It has a moment of inertia I. So if I do it that way, I can use the work energy principle. Work is the change in kinetic energy plus a change in rotational kinetic energy plus the change in gravitational potential energy. And so this is my y equals 0. So I'm going to call this V1, omega 1, and then it'll be down here, omega 2, V2. And V1 equals 0, omega 1 equals 0. So there's no work done because the only forces are gravity, but that's in the gravitational potential energy. The normal force is perpendicular to the motion, and friction actually doesn't move, right? The friction force is the point of application moves, but the force doesn't move, so there's no work done by friction. So I get 0 is K2 minus K1 plus KR2 minus KR1 plus U, let's call it U2 minus U1. And so K is 1/2 mv squared. K rotational is 1/2 I omega squared. U is mgy. So down here I'm going to get, since U2 is 0, it ends at the bottom. That's 0. Since it starts from rest, this is 0 and that's 0. So I get 0 equals 1/2 mv2 squared, that's the kinetic energy right there, plus 1/2 I omega 2 squared, and then I get minus mg, the change in y. So the change in y right here is going to be this distance, but this is s. I get s sine theta, right? Because when the distance s, then this height is sine theta, s sine theta. Okay, now if it's rolling without slipping, I can say omega 2 is equal to V2 over R, right? That's my rolling without a slipping equation. So if I put that in over here, I'm also going to go ahead and multiply everything by 2 and divide by m. So I get 0 equals V2 squared plus I over m V2 squared over R squared. That term looks familiar. Minus G2 GS sine theta. Now right here I can factor out the V squared. So I get 0 equals V2 squared times 1 plus I over m R squared minus 2 GS sine theta. And now I'm going to solve for V2 squared. I'm going to add that to the other side and divide. So I get V2 squared equals 2G sine theta over 1 plus I m R squared. Now, if you think about the kinematic equation, this is going to be equal to V1 squared plus 2 AS, right? That's the kinematic equation. It says the final velocity squared, it's initial velocity squared plus 2 times acceleration times s. Well, look right here. I have a 2 and an s. And V1 is 0, so 2 and s, if I take everything else out, I get G. I put it there. 2 and an s. I was factoring out the s from the sign. I get G sine theta over this is equal to A. So I get A equals G sine theta over 1 plus I over m R squared. And that's exactly the same as what I got before. I kind of like the other way better because it's just more fun. But this is a way that might make more sense to some people too. Okay, that was just a little side project. back to our chapter summaries. I just want to do this derivation. Hope you enjoyed that. And so I'll put, this is part of my summary of introductory college physics. I'm using Halliday, Resnick, and Walker, 9th edition. I'll put a link to all those down below if you want to see that too. I'll put this in that playlist too. So I'll talk to you later.